Every Linux machine on Earth just became vulnerable to a 732-byte Python script. And the most alarming part of that sentence is not the size of the script. It is the fact that the vulnerability it exploits has been sitting inside the Linux kernel since 2017, invisible to every human security researcher who examined that code across 9 years, until an AI agent found it in approximately 1 hour of scan time. CVE 2026-31431. Named copy fail by the researchers who discovered it, is a confirmed privilege escalation vulnerability affecting every Linux distribution running kernel code updated after 2017. Debian, Arch, Ubuntu, Red Hat, SUSE, Amazon Linux, every major distribution and hundreds of minor ones. The Linux kernel team has confirmed the vulnerability. CISA has added it to the known exploited vulnerabilities list. CrowdStrike has confirmed active exploitation in the wild, and the proof of concept exploit code is publicly available on the internet, meaning that anyone with basic technical knowledge and access to a Linux system can use it right now. If you run a Linux server, manage Linux infrastructure, or use Linux as a desktop operating system, you need to understand what this vulnerability is, how it works, what you need to do about it, and what its discovery reveals about the future of cybersecurity before you read another line of anything else today. Start with what the vulnerability actually does, because the technical description matters for understanding both the severity and the limitations of the risk. Our copy fail allows an unprivileged local user to write 4 uncontrolled bytes into the page cache of any readable file on a Linux system, and use that write access to gain root privileges. Root access on a Linux system means complete administrative control over everything the operating system can do. It means reading any file on the system regardless of permissions, writing to any file, installing any software without restriction, modifying any system configuration, deleting any data, creating new user accounts with any privilege level, intercepting any network traffic passing through the system, exfiltrating any data stored anywhere on the machine. Everything that the operating system can do, the attacker can do, after exploiting this vulnerability from a starting position of having no special privileges whatsoever. The jump from unprivileged user to complete root control through 4 bytes of carefully placed data is the essence of what makes this vulnerability so technically significant and so operationally dangerous to every Linux environment where it remains unpatched. The mechanism that makes this possible involves a component called ONC-ESN, which stands for Authentication Encryption Extended Sequence Numbers. The specific function of ONC-ESN in the kernel's cryptographic infrastructure is less important for understanding the vulnerability than understanding where it sits in the overall system architecture. ONC-ESN lives behind Linux's AF-ALG interface, which is the kernel interface that exposes cryptographic algorithms to user space applications so that those applications can use kernel-level cryptographic functions without implementing them independently. When ONC-ESN processes cryptographic operations, it writes 4 bytes of scratch data into what it expects to be a crypto output buffer allocated for that purpose. Under normal circumstances, this is harmless, functionally invisible, and exactly what the code is supposed to do. But because of a logic flaw in the AF-ALG splice function, that output buffer can accidentally point into the page cache of a read-only file rather than into the intended crypto buffer. The page cache is the kernel's in-memory representation of file contents, the working copy that the system reads from when applications access files. Writing into the page cache of a read-only file means modifying the in-memory version of a file that should be completely protected from modification by unprivileged users under any normal operating condition. The specific file that the public proof of concept exploit targets is the SUE binary. SUE is present on every Linux distribution without exception, and allows users to run commands as root or switch to the root user account entirely. By writing carefully chosen bytes into the page cache of the SUE binary at the correct offset, an attacker can modify the in-memory version of that file in a way that bypasses its authentication checks when it next executes. When SU then runs, it runs the attacker's modified version from the page cache rather than the original unmodified version from disk. The authentication check that should require a valid root password before granting elevated access no longer functions correctly in the modified version because the bytes that implement that check have been overwritten. The attacker gains root access without providing valid credentials. The entire privilege separation model that forms the foundation of Linux security has been bypassed through 4 bytes placed with surgical precision into a specific location in memory using a Python script small enough to fit in a text message. The discovery story behind copy-fail is in some respects more significant for the long-term security landscape than the vulnerability itself, because it signals a fundamental change in how vulnerabilities will be found going forward and what that means for the pace at which previously unknown vulnerabilities will surface. The security research firm Theory deployed an AI agent and gave it a single hypothesis expressed as a natural language prompt. The prompt directed the agent to examine whether the splice functionality in the kernel could deliver page cache references of read-only files to cryptographic transmission scatter lists, essentially asking the AI to investigate whether the specific class of bug that became copy-fail was present somewhere in the codebase. The AI agent took that prompt and in approximately 1 hour of scan time identified the specific code path where the vulnerability existed, confirmed that the vulnerability was exploitable, developed a working proof of concept exploit, and produced documentation detailed enough to publish publicly alongside a dedicated website for the vulnerability. The going rate for a universal Linux privilege escalation vulnerability on the gray market ranges between $10,000 and $7 million, depending on reliability and breadth of impact. This particular vulnerability affects essentially every Linux installation on the planet running code from the past 8 years and was found by an AI agent in 1 hour following a single conversational prompt describing the vulnerability class to investigate. The confirmation process that followed the AI's discovery validated the finding completely. Initial skepticism in the security community questioned whether the AI had found something real or produced what researchers call AI slop. Plausible sounding, but technically incorrect vulnerability, reports that waste time and erode trust in automated tools. The Linux kernel team reviewed the finding and confirmed it. The vulnerability was traced back to commits in the kernel from 2015 and 2017 that appeared entirely unremarkable at the time of their introduction and survived years of code review, security auditing, and automated scanning by tools that were not specifically looking for this class of interaction between the AFALG splice function and the page cache. CrowdStrike's confirmation of wild exploitation arrived shortly after public disclosure, compressing the timeline between disclosure and known active use to a degree that leaves little room for extended patching windows. The critical limitation of copy-fail that prevents it from being a remote code execution vulnerability in the most severe possible category is that it requires local access to exploit. An attacker cannot use this vulnerability to compromise a Linux system directly from the internet without first gaining some form of foothold on the target machine through a separate initial access vector. That foothold could come through many routes that are well within the capability of motivated attackers. A compromised web application running on the server with limited system privileges, a successful phishing or credential stuffing attack that provides SSH access with a low-privilege user account, a different vulnerability that allows initial access at a non-root privilege level, exploitation of a misconfigured service that exposes limited shell access, an insider threat or compromised contractor account. Once any of those initial access vectors are available to an attacker, copy-fail transforms that limited foothold into complete root access in seconds using a script that requires no specialized knowledge to execute. The local-only requirement reduces the risk to individual desktop users who control their machines entirely and are careful about who has access. It does not reduce the risk to servers, cloud infrastructure, shared hosting environments, multi-user development systems, or any environment where multiple people have accounts or where applications running with restricted privileges could be used as a stepping stone to privilege escalation. Here is exactly what you need to do based on your specific situation. If you are a Linux desktop user running any distribution with a kernel updated after 2017, check your distribution's security advisories for CVE 2026-31431 immediately. Debian has issued DSA advisories for this vulnerability. Red Hat has issued security advisories for RHEL and all related distributions. Arch Linux has pushed kernel updates through the standard rolling release package manager. Ubuntu has released security updates through the standard package management path. The commands you need depend on your specific distribution, but the action is consistent across all of them. Pull the latest security updates and apply them without delay. On Debian and Ubuntu-based systems, run apt update followed by apt upgrade in a terminal. On Red Hat, Fedora, and CentOS Stream systems, run DNF update or yum update depending on your version. On Arch and Arch-based distributions, run pacman, su, to synchronize and upgrade all packages. After updating, reboot your system. This step is not optional. The kernel is loaded into memory at boot time, and a running system does not automatically switch to a new kernel version when that kernel is installed. The old vulnerable kernel remains active until you reboot, and the system loads the newly installed patched version. After rebooting, Verify that the updated kernel is running by checking the output of unaim, R, and confirming that the version number matches the patched release documented in your distribution's security advisory. If you manage Linux servers in any capacity, whether those are physical bare metal servers, virtual machines in a private data center, or cloud instances running on any major cloud provider, the patching priority is higher, and the process requires more careful coordination. Enterprise Linux distributions, including RHEL, CentOS, Amazon Linux, and SUSE, Enterprise Linux typically routes security updates through a staged validation process before pushing them to production systems. For copy fail, given the known exploited vulnerabilities designation and CrowdStrike's confirmation of active wild exploitation, the standard staged rollout timeline should be compressed to the shortest interval your organization's change management process allows. Apply the kernel patches following your vendor's security advisory. After patching each system, verify the updated kernel version is active and document the patching action for compliance and audit purposes. For systems that cannot be rebooted immediately due to workload constraints, assess whether compensating controls, such as enhanced monitoring for privilege escalation attempts, can reduce the risk during the window between patching and reboot. For organizations running containerized workloads on Kubernetes or other container orchestration platforms, the host kernel is the critical patching target, rather than the container images themselves. Containers share the kernel of the host operating system, which means that a privilege escalation vulnerability in the kernel affects all containerized workloads running on that host, even if those workloads are themselves fully up to date. The patch must be applied to the host operating system, and the host must be rebooted for the protection to become active. Kubernetes provides rolling update mechanisms that allow you to cordon and drain nodes for patching while maintaining workload availability by scheduling pods to other nodes in the cluster. Work through your node groups systematically, patching and rebooting each node while maintaining sufficient cluster capacity to sustain your workloads throughout the process. The broader lesson that copy-fail teaches extends significantly beyond the specific patch that needs to be applied to vulnerable systems today. An AI agent found a 9-year-old privilege escalation vulnerability in one of the most scrutinized open-source codebases on Earth in 1 hour by examining a specific vulnerability class with focused attention and the ability to reason about complex interactions between kernel subsystems at a depth and speed that human researchers cannot match through manual code review. The Linux kernel has millions of lines of code reviewed by thousands of contributors from major organizations, including Google, IBM, Red Hat, Intel, and many others, all of whom have strong technical expertise and significant financial incentives to find and report security vulnerabilities. If a 9-year-old privilege escalation vulnerability can survive in that environment until an AI tool with the right hypothesis examines the right subsystem, every other complex code base that has accumulated years of committed code from multiple contributors should be treated as potentially harboring undiscovered vulnerabilities of comparable severity, waiting for the right AI agent with the right prompt to surface them. The security community is at the beginning of a period where AI-assisted vulnerability discovery will systematically surface vulnerabilities that human researchers missed across decades of code review, and automated scanning with tools that were not designed to reason about complex multi-subsystem interactions. The organizations that build patching pipelines capable of responding to this accelerated disclosure pace, that maintain current patch levels as a baseline operational requirement rather than a periodic maintenance task, and that monitor for exploitation attempts against known vulnerabilities will be the ones that manage the transition through this period without the kind of incidents that follow from being caught with known vulnerabilities unpatched when active exploitation is confirmed. Patch your Linux systems today. Check your distribution's security advisories. Apply the kernel updates. Reboot to activate the patched kernel. Verify the version. And if you manage any environment where Linux systems have fallen behind on patching, treat that backlog as the liability